So now welcome to this course on elements of data analysis. Seems to be somebody out there who tries to get, but the door was still open, right? Anyway, so welcome to this course. As you can see, we are quite a lot of people. If we would have turned out up to be a small amount of people, maybe we would have made this a little interactive group. Now we have to try to be as interactive as possible. But I wrote to you that you don't need to bring your laptops, because obviously if we are over 40 people, there's not much chance of everybody typing on their laptop. So the format that I now thought is that I present a bit showing you here how things are done, or I have written down what I'll do, so you can later read it all up. You don't have to take now notes. And then you can later see and maybe try to recapitulate or do the things on your own later in the course. Maybe we also will make some exercises and so on. The whole length of the course, I don't know how long it will be. It depends a bit on how much material we have to cover. So you're all welcome to tell me what you would like to see covered. Give me feedback of where we should aim. I have now sort of made up my mind what I want to teach you in the first 1 or 2 lectures, and we are free to see where we head afterwards. There's basically different directions into which we can head. One thing is that we say this will be an R course, where you learn the R statistical programming environment. Another direction we can say is with a general basic data analysis course, where we go back through all the stuff that you might have once heard in your undergrad statistics course when you were still sort of too unfamiliar with real data that you couldn't really follow. Learning about a t-test in your first year of undergrad is maybe very different from actually having taken your own data and then having to figure out what it really does. So what I think would be quite valuable is to revisit all these concepts that you supposedly all have already learned in your undergrad time, and go through them again and really try to understand what's behind of them. And do this not by doing a lot of formula and mathematics, because we can do something better, and I hope I find time to demonstrate this a bit today. We can do simulations. Simulation means lots of statistics is about asking what would we get if we had infinitely many replicates. This is maybe the first misconception I want to start with. Usually when as a statistician you talk with biologists, my impression is most biologists have the idea, statisticians were the people who always tell us that we need more replicates. Obviously, with the advice that many of you got, it's simply because you talk to lazy statisticians. The proper job of statistics is to figure out precisely how much data you need in order to take some data and tell you either this was way too little data, you can't say anything, or this was way too much data, you have wasted time and effort and money. Preferably tell you this before you do the stuff. But one thing we can do is we simulate the idea that we would have very much data, and then we try to boil down to what would happen if we wouldn't have had thousands of data points but only 5 or 10 mice, or perhaps only 2 or 3 mice. And we'll see this in a moment, how powerful and how much easier statistical concepts are to understand if you don't try to explain the math, just simply demonstrate. Imagine you would have this huge pile of data when the answer would be absolutely clear. And now let's go down to the realistic case that we have only 3 or 4 data points. What can we still say and what can we not say? We need example data to demonstrate this. My idea for example data was first to take some laboratory data, something from your practical everyday work, but there's first, some people might be familiar with a certain kind of data and others aren't, and then they can't quite follow. Second, the more important part, I might not be familiar with it, and then I talk nonsense. So in the end, I thought I'd go for a data set which is something that you all might have a good intuitive grasp for, but which might be not that exciting from a molecular biology point of view. We are taking a biometry data set, talking about the height of people and how height depends on sex and age and things like this. What I found looking for some nice free data was in the end this thing here, the National Health and Nutrition Examination Survey, which is done every 2 years by the CDC, so the Center for Disease Control. What they do is they take, obviously being the American main health authority, they are interested in understanding the main health dangers for the American people, which is most importantly the obesity epidemic. So they take a random sample of 5,000 representatively chosen Americans and examine them. They ask them lots of questions, they measure them, they make a little cursory health exam, they even take blood works, and most of this stuff is openly available. What I've decided to go for now, just to quickly show you where the data comes from, what we are looking for is the NHANES. Is this big enough for everybody to see, by the way? We are looking here at these questionnaires. I took the questionnaire from 2015-2016. You see there's lots of stuff, dietary data, examination data, We'll start with the demographics data. So I have downloaded this data set here, 3.6 megabytes of data, and let's look a bit at this. Before I now get into the thing, 1 second pretext. There is basically 2 areas of data science that I want to cover, and I think one of the most important things is that you understand that that all data science falls into these 2 parts, and you always have to switch between the 2. One is the so-called exploratory data analysis. So exploratory data analysis, let's write it down, or often just called EDA, and the other is inferential statistics. Inferential statistics is the thing that you all know, that people usually associate with statistics. That's calculating p-values. EDA is the other thing. You get a huge chunk of data, huge tables, maybe several tables, and you want to know, is there something in there, something surprising? How do you explore data which is simply too big to fit into your Excel data? How do you best plot with it? And this is now what I want to start, and my idea was simply, I'll show you a bit how I examined this health data and how I looked for interesting things, just a random thinking, this might be interesting, that might be interesting. It might not be that interesting because it's just simple health data, but it's an easy way to follow, and it's a good way for me to make you familiar a bit with concepts that you use in data science, and also to make you roughly familiar with our workhorse here, the R statistical programming environment. So R is a language to program statistical analyses, and there is a lot of advantage of having learned a little bit of R in order to simplify analyses which are very hard or nearly impossible using Excel or something like this. Also, it's much less error prone. Why this is of advantage is something which might not become too clear from the simple examples that I show you now, and where you all will say, sure, I could do the same in Excel. But so bear with me, and the really interesting stuff that you might say, oh, I wouldn't have known how to do that in Excel. It might be that we get to there only next week. But let's start with something simple so that you can all easily follow. The other point that I want to say is my goal is not to make all of you expert R programmers. My goal is to make sure that you have a clear feeling of what you can do with biostatistics and biological data analysis, so that if you have this data, you can decide it might be worth for me to learn this. You can decide it might be worth to collaborate with something, but you shouldn't be in the situation where you have some problem which would be easy to solve, but you don't even have the idea that this is something you could ask a bioinformatician about, which is actually way more common than you think. Typically, I've noticed this when planning these courses, the big bosses told me, teach them about omics, explain to them how to analyze complicated RNA-seq, riboprofiling, ChIP-seq, whatever combination data. And my practical feeling is half of the questions that people come to me and ask about, I have this Western blot with this 3-time factorial design, and I have this simple table, but I don't know what to normalize with which. So yes, there's a lot of standard lab experiments where the analysis is not as obvious as it is. So what do we start with? What I will now do, the reason why you don't have to take notes is because I wrote down here a lot of stuff already, also for me to prepare what I want to show you, and you can read this up later. I'll send the link around over the email list afterwards. So what I will do is, and for now, don't try to read this, it's too much to read. It will only flash up from time to time because I always have to copy and paste from there in case I forget what I wanted to do. So what we start with is in R, the way how it works is you have up here, you have an area where you can write your code, and down here in the console, the code always gets executed. So I have it up here, I press Ctrl Enter, and the word appears down here at the bottom. And let me make sure that we start with a fresh session. Sorry, that was the wrong button. Session, restart R. Now I loaded a package with additional stuff for R. And what I will load is something called the tidyverse. Now I've forgotten my book. So R is a 30-year-old thing. It has, and over this 30-year-old, it got changed, and people added stuff and deleted stuff and changed the way how you use it. And if you want to learn nowadays R, you have to be a bit of an archaeologist. And you have to learn how people, R users, did it in the 80s, in case you want to work with old stuff, or how we did it in the 90s, or how we did it in the 2000s. And this has become really cumbersome and made it very hard to get in. A couple of people tried to tidy up this whole stuff, and they came up with this idea, let's tidy up this universe of way too many different ways of how to do one and the same thing in R, and present one small thing which they call the tidyverse. So let's load that tidyverse thing, which lists us here all the components which we want. We want to ignore this. And now usually, I guess most of you have at least worked a little bit maybe on a sort of command-based stuff. If not, then you at least will not be that surprised that the way how it works is that you type a command and then execute it. In this case, I start with, how was this called? XPT. This is why I always need to look over. It's in Haven. Yes. Let me copy and paste this thing here. So here I call a function called readXPT. That's of course things which you have to do with it, because the data that they have, they use another statistics program, not R. They use something called SAS, and it uses another format, so we have to convert it. So don't worry about this, why the command to just read the data is so complicated. Session, set working directory, choose directory. Where have I put all this thing in work? Course. What we do here is simply load the data table. This data table demographics I. And now I can look into it and here see how this looks like. There is lots of stuff like a sequence number, like the age of the participants, the birth, the country of birth, and things and so on. I load the other table that I wanted to see, this one here. And again, and now we can do our first complicated operation, and that's a typical thing. That's one of these typical things which you always stumble over once you have it for the first time. Have a look into this one. It's a bit annoying to work with this small screen. It looks much easier on my big screen. We have these sequence numbers which label the respondents, and we have here another sequence number on that one. And we want to merge these two tables. Now we have two tables from the same survey, but they probably don't have the subjects in the same order. Now if I want to compare age with height, and age is in the first and height is in the second table, I have to make sure that I map the rows from one and the rows from I map the rows from one table and the rows from the other table, that I always put rows together from the same subject. This is now something of a third part of bioinformatics that I've forgotten here, and that stands at the beginning of all of them, called data wrangling. Data wrangling means whenever you get data, it's never in the format that your software wants. You always have to convert it. Your software wants a table with rows, you have a table with columns. Your software wants gene IDs in ensemble format, you have it in entrée format. Three-quarters of bioinformatics is wrangling with the data of bringing them into the right shape. And it's worth learning at least a little bit. And now I show you a very simple wrangling operation. We have these two tables. I want to bring them into one table, and I want to join them. Now I won't explain you what the difference between an inner join and an outer join and a left join and a right join is. For now, let's just say it's a way of joining tables. This table and the other table. And I have to tell it, let's make it the demo table first, and the, how was the other, body measures, that's what was body measures examination, that's what BMX stands for. Now I have to say how it should join them. It should always join by by the sequence number column, which tells us which rows belong together. If I now run this, it tells me now I have a new table here with 9,544 rows, 72 columns, and all these data with these strange abbreviations. It's hard to understand. I find it hard to work with DMDHSCE. Obviously, these people with their 500 items questionnaire and so on, they needed to come up with some scheme of crawling their column. What they did, if you look for a moment here, they have given a little explanation for each of them. They have also given us a long explanation for each of them. Here, for example, is a documentation thing which explains us exactly for each of these cryptic things. For example, that citizen status has a 1, 2, 7, or 8, depending on whether it's a US citizen or not. So the first thing I've done when I prepared this lecture is to change all these numbers in strange abbreviation into something which we can read. I quickly copy and paste this simply. So, just 1 second. Here is my lengthy command which I use to insert it. And again, I'm jumping just here in the middle of a big analysis just to give you a feeling how these things typically look like. Let's make my picture a little bit larger, and here you see this is now a long command, and after I followed this command I now have a new variable here which is called just enhance, and if you look into it, it now looks much more manageable. I now have here a select column of 12 different columns which I call age, sex, height, weight, ethnicity, education, and born in the US. And I have replaced all these 1s and 2s and 3s by something which I can read. How have I done this? Here you see how this typically looks like. In this tidyverse thing, the central element is a table, how they call it a tibble, to distinguish it from the old style tables. And I take these tables and I always hand them on from one operation to the next with these funny arrows. Here, for example, I make this join that I've just shown you to put the tables together. And now I use the select command, which there's only a couple of 5-6 commands which we have to memorize to understand today's lecture. The select command means select the following columns. I don't want all columns, I only want the columns which are called second, root age year, rear age sinder, Bingsit, Bingswit, and so on. I changed them, and while I selected them, I changed them all into something which I find more pronounceable by looking up in the big documentation what they mean. So we have now the age in year, the sex, which is male or female, the height in centimeters, the weight in kilograms. Note that the CDC uses metric systems despite being in the US. The ethnicity, the education, and whether the subject has been born in the US or not. As you've seen, they use these strange numbers. I recoded the numbers here by just typing it. Whenever I see a 1 in the ethnicity column, I want it to be relabeled to Mexican, 2 is Hispanic, then there's white, black, Asian, and other in their logic. And let's see what we can now do with this kind of things. The first thing we might ask is, what age survey have people actually? What age range have people actually surveyed here? So I take my big data table, and the process which you will now see over and over, I hand it over to ggplot, the plotting facility of R. So it will always be take a table, hand it to ggplot, and then I say a certain plot type. Here you see all my plot types, and I now, because I want to see this, I take a histogram. I'll explain later what this ACE means, and now I simply, of what do we want to see a histogram of age? So, and now here we can see what age ranges. So the survey really started with newborns, went all the way through all kinds of different people. You see it's 5,000 people, so maybe 1,000 of these, and here at the very end, we see this spike. We can already learn about oddities of the data this way. Who finds this odd here, this spike? So many 80-year-olds. Turns out if you look up in the documentation, they said that everybody aged above 79 will be coded as 80, no matter how old they really are. I was a bit surprised. Why would they do that? Turns out they have a very good reason. They have so few really old people in the survey that they were worried if they give the exact age, people might be able to identify the subjects. So whenever they had the feeling that people might identify and realize, because that would be very embarrassing, your grandparent tells you, I filled out this funny survey of the CDC, and when your grandson goes at the database next to me, my grandfather is an immigrant, he has this school level, and he is 83, and finds the exact 3 rows which might be him. So these are things you have to think about if you make such data public. What can we do next? So what you've seen here now is this very easy thing, which actually is a quite nice thing about R, that typing the commands is a bit of cumbersome, but once you've typed them, you can easily change them. I might say, yeah, I really want a histogram of age. Let's take a histogram of height. How tall are these people? That's how tall they are. Now I look at this, and it looks sort of bimodal. There seems to be here a big pile of people who are sort of between 160 and 180. And there's this left shoulder of people who are strangely small. Probably these are not all dwarfs, but as we've seen before, they also survey children. Actually, if you look into the documentation, they have a lot of difference where they say people below the age of 18 were asked this question, above the age that question. But what we now want to see, how does height depend on age? The workhorse of data analysis is the scatter plot. Who knows what a scatter plot is? Yep. Funnily, nobody knows it under this name, but everybody of you knows what an XY plot is. And they call it a point plot, Guillaume point. In Guillaume point, we just have to say what we want to put on the x-axis, namely the age, and what do we want to put on the y-axis, namely the height, and then it will draw a little point for each plot, for each row in the table. So I do this, and now I get this thing here, which you can see makes a lot of sense. People seem to be growing up to age maybe 18, 19, and then they seem to be in this constant height. Once we have this, we can now refine our plot a little bit. Let me first to refine it a little bit, make this here a bit more. So when working with programming languages like this, there's a lot to be gained from putting spaces and putting indenting and sort of spreading out your command when it looks a bit longer and more intimidating, which might be good or bad depending on whether it's your own code or not, but it's also easier to find stuff. So the first thing I don't like here is that all these dots are so large that they sort of blend into each other. Let's make them much smaller. Now, as you can already see, these points, they can be described by certain aspects. There's the x-coordinate, there's the y-coordinate, there's, for example, the color. If I say color is red, then you can guess what will happen. They're all red. Not that useful. But let's say size is, I think the default size, this I think is size 5. So let's see how size 1 looks like. Still a bit small, a bit larger, 0.3. Now I have these dots. Next thing, maybe there's lots of points plotted on top of each other, which I can't quite distinguish. I don't know whether there's maybe way more points here than up here. Let's just make them slightly transparent. Now I will show you that later. There's a little table which gives you a list of all the different things that you can change in a plot, and it will tell you transparency is changed by the parameter alpha. Those people who've ever worked with image and with Photoshop or something like this will know that the transparency channel is called the alpha channel in this linguistics. So now the thing looks a bit nicer, but we've now seen how height depends on age. There's one more very important covariate that tends to determine height. Who knows that? Gender, or as we say in biology, sex. I've been explained by various people that that you only have to say gender if you're doing humanities, and in biology we do sex. We say sex. I'm a physicist, so I don't know about this, but I've labeled the column now sex. Also, Wikipedia confirmed me in this claim. So I simply say sex is, sorry, the other way around. First, what I want to determine, color equals sex. This now tells ggplot I want to change to let the color of the point determine on sex. ggplot is clever enough to notice that I have two different values of sex, so I probably want to know two different colors. It is not clever enough to know the current customary assignment of baby colors, of baby genders to colors, so the males are red, the females are blue. Doesn't matter. So now we can see how we can already learn a lot of things, some things which I didn't know. You can see here how the red ones are sort of generally above the blue ones. It seems that really most men are taller than most women. Maybe we can check this by just looking around here. What I wasn't that clear on is that this difference really only happens after the age of 17 or 16. If you look at the children, it seems to be completely intermixed. So these are things which we now, and this is what I call exploratory data analysis. I haven't done any t-tests, I haven't done any p-values, I've just done hypotheses to get familiar with this data and see what I can do with it. And for this, what I needed to do is bring all the data in one big table and then now just show fantasy and look at different things. So what's the next thing we might look at? We might now wonder about, one thing we might wonder about is, of course, weight. As I said earlier, the CDC, as the American Health Organization, is worried about the obesity epidemic, which is undoubtedly happening in many industrialized countries, so they asked for weight. So let's change our plot to plot age against weight. So I take this whole thing, just make a copy and paste, so that I have the old one still, and now I have the new one, and now let's do this time, put the height on the x-axis, and the weight on the y-axis. And the rest I leave as it is. And let's see what we get now. Let's click here on zoom to make this nice and large. So, now the first thing is we see two different clouds, obviously. To the left, the women who are only typically around 150 to 170 centimeters tall. To the right, the man who in America seems to be in this area. What we can also see is a quite impressive range of weight values, going here from these average 50 to 60 up to our maximum weight in the survey, which was 200 kilograms. Again, we can see that among children, height and weight doesn't seem to differ that much, assuming that these are the children. Now on these points we can't see who are children and who are adults. So it might be good to have two different plots according to that. Again, once you're familiar with R and ggplot a bit, you will know that whenever you want to spread your data according to the data on several plots, you can use a thing which is called faceting. Faceting means I just tell it something which I want to use to spread the things. In this case, whether the age is, I now divide it adulthood with age 20. So everybody at least 20 will be an adult, otherwise not. Let's see if this works. Now, as you can see, it now has given me two plots, which are now labeled according to this faceting here. False means this condition here is false. The age is not greater or equal than 20. True means that it is. What happened now? Oop. Good zoom. This looks a bit worrying. I didn't want that much. Oh, it has. Now I've closed the wrong window. Luckily, RStudio is rather generous with these kinds of things, and usually doesn't forget the whole thing. This time it has. No worries, that's what why I plotted this whole thing. So And here was my code to load the data. And my code to load this thing here. Now, as usual, of course, the first thing you always have to do is to make sure you're in the directory where all your data is. Session, set working directory. I think I put it work course. Execute everything. Now we're back at where we were. What did I do? In Haynes, let's see how quick I am at typing. To ggplot, then hand it over to say that I want points, and where I want an stat, I want to set x is the height, y is the weight. What else do we have? What else did we have? Color is the sex, and size is 0.3. Alpha is also 0.3, let's say 30% transparency. You might by the way notice that some things are in these aesthetics arguments, others aren't. If you spot closely, the difference is here these are all table columns and they change from point to point, and these are constants. This is the reason why some are in here, which means these are depend on the data and the others don't. So now, as I said, I wanted to remove the children. Another way to do this is actually to change the data set. Here, you remember, this was my data. Now I can simply use again one of these commands to manipulate tables. And I told you there will be only 5 commands which you need to understand for today. We already had select to select which columns we want. We have briefly used inner join our tables. Now we use another very useful one, which is called filter. Select selects columns, filter selects rows. Don't worry, I'll show you a little overview A4 page which nicely puts these things together afterwards. So filter selects rows. I can now select which rows I want. Remember here, let's keep for the moment our total data table is 9,544 subjects. Now if I filter them, I might say I only want to keep those which are at least 20 years old. And if I do this now I have only 5,000 data tables. So this is something very useful. You have data, you want to quickly subset the data, so you just say here filter. And then I can now take the filtered data and just say hand this filtered data on to ggplot, always with this funny pipe symbol, that's how we call it. And now we see here this thing, which is now only weight over height. What we can see is that weight seems to increase with height, which makes it hard to compare. Is this person here now more unhealthy than that person or not? As you all know, the standard answer of the epidemiologist is that you have to divide the height, you have to divide the weight by the height squared to get the so-called body mass index, and then we supposedly get something which is more useful. So let's try this out. Again, this is very simple. I say here my y is my weight, and I divide it by the height squared. Let's see what we get now. Now, it seems that the y-axis doesn't depend that much more on the weight. Those people who are familiar with the body mass index might now be wondering, why are they so small? But remember, the BMI formula says that you should divide by the height in meters, but our height is given in centimeters. So let's fix this. Divide the height by 100 before calculating. Now we can see the actual BMI values. Those people who are familiar with this measure, which is probably most of them, will now know what the values mean, how they are usually interpreted. For the other ones, I will sort of hand it in. I've already told you, we've already seen different geoms. You've noticed by now a geom is a different style of plotting. We've seen the geom histogram at the beginning. We've seen the geom point right now. Now I'll add something which is called the geom horizontal line or H line. It's that used to add lines. So I add now a line at 18.5. This is according to the WHO consensus, the boundary between an underweight and a normal person. 25, the boundary between a normal and an overweight person, and 30, the boundary to pathological obesity. Using this now, didn't work. Unexpected, here you see unexpected closing parenthesis. Luckily, this thing can tell us here always, you might notice whenever I put the cursor on a parenthesis, it highlights the other parenthesis. This is very useful because you keep missing parentheses, so this one seems to be too much. So, that's how it looks like. Most people are, it seems that about half of them are overweight, maybe probably more. How can we now pinpoint this? Let's stick with this, but first some aesthetics. It's important to make your plots pleasant to look at, and I really feel a bit appalled by this heavy black line which completely distracts the eyes from points. It's actually not just aesthetics, but it's important to make sure that you make your plots such that the eye doesn't get drawn to irrelevant features. So how do we make this less intrusive? Well, you all know the answer already with the alpha argument again, to say our error should also be a bit transparent. Looks nicer. So, what's the next thing? We wanted to, not everything can be has to be done by graph. If we just want to know how many people are underweight, overweight, or whatsoever, we can also do other manipulations. And now just to go on in my aim of giving you a little flavor of how different things of data manipulation works like, let's try to categorize everybody in this data set by their body mass index according to WHO standards. So the first thing is I'll add a new column. Now comes the third new command besides select and filter, mutate. It's the strangest named one among all of them. I have no clue why Hadley Wickham, the creator of this thing, called it mutate. Clearly he's not a biologist and probably has some strange ideas what a mutation is, but to him a mutation of a table means adding a column or changing a column. We'll add a column. BMI is weight over height divided by 100. Now with this new extra column, we wouldn't have to write out the whole formula up here. We can simply write BMI from now on. So here, now you see, we have now, oh, it doesn't show them because my screen is too small, but here it tells us this. Now, with all this, we can now, of course, go on and classify the people.
Shouldn't you do like square of the height?
Right. Thanks. And to classify them, I do another mutate. Call them now class. And now, again, this is the kind of things you now think, how do I divide up a range of values into different categories? This is one of these things which are hard to Google if you don't already know what the answer is. Luckily, I know it, so I only had to Google how does the cut command in R work. And the cut command in R, which of course I've forgotten already and I don't want to look up now, so I simply press F1 to see the help here. To read up, and just to remind me quickly, I'm supposed to give a list of, to first give the vector I want to cut, so my vector BMI. Now I'm supposed to give a list of breaks. What are my breaks? And don't try to read this so quickly now. It's just where I want to cut. My first category is from 0 to 18.5. The second is from 18.5 to 25. The third from 25 to 30. And the end is from 30 to open end. And for open end, I simply write infinity. Let's hope we don't really need this. And now, how do I want to call them? Underweight, normal, overweight, and obese. This is of course, whenever you make such courses with data, you have to be careful to with data about people. You have to be careful to not offend anybody, but luckily A, it's all anonymized, and B, it's our thing. Now we have here this thing, class. What we can now do is that we have this, I can hand this over to my next step. And my next step will now be that I use the, I think it was called count. And the count command simply counts how often something happens. For example, I can count by sex, and it then just tells me how many males and how many females is. I can count by class, and then it tells me how many people are of each category. Or I can make something which is called in statistics a cross tabulation, which is a very fancy word for simply this here. We get a counting according to two criteria. We now see how many males are underweight, how many females are underweight, which percentage of males and females is overweight or obese or whatever. I could now, of course, if I now don't want to read these things, I could now be fancy again and introduce you to yet another geom, this one here, statics. Let's say x is sex and y is just the density, and color is class. What might this now do? You can guess. You can also simply look at it. Right. This is what we now get. Didn't quite work as I wanted. First I should use fill, and second I should have omitted. I don't want to count. I want to let a geom bar do the counting. Now, here we go. The counts of males and females in the different classes. And now you can sort of read off things from this. Now, of course, at this point, we now might feel worried about, are these WHO classes really that meaningful? Should we really go divide things exactly by 25? So in a way, this is the kind of plot that I would typically not advise people to use, because it is a premature reduction of information. We could as easily, in the same size of a plot, show a more informative data, and I show you this here, by using the let's use the histogram class. And this time I put on the x-axis the BMI and use the color for the sex. Now I see it like here. Oh, sorry. Now we see one annoying thing that the histogram function does. It stacks the bars. So this is a bit hard to read. You see the blue ones are the female, the red ones are the males. Maybe I don't want them stacked, I want them next to each other. So I have to say, and I think I always look this up, position is identity. How do you find things like this out? You look at these things and say, this histogram doesn't look like the histogram I want. I want a histogram that looks like this. Was fehlt? Identity. Let's see if that now worked. Now it has plotted them on top of each other. Of course, we can't see this now, so fill and let's click this so that you can read it better. This one, position, and alpha is 0.3. So I've changed color to fill because I want them to be filled. And now I see here these two histograms plotted on top of each other, semi-transparent, so that we can see both. And now it's quite easy to see that overall the male histogram seems to be more peaked than the female histogram. The female one goes here is sort of a bit wider. Of course, we can use again the same way how we used it in the. Next time we need this beamer with a bigger screen, because I find this here really cumbersome to always move this back and forth. I can change here from a horizontal to a vertical line and do the same as what we had before. And doesn't work again. What's wrong now? E-line intercept. Who sees the mistake? And now I should have hoped to see geom requires the following x-intercept, it's called now. Now again, we have plotted these here, and now we can read off in this histogram, sort of can ask, what is the ratio of the area to the left of the obesity line and to the right of the obesity line to judge how obese the people are, and also we can still see whether they are just barely above the WHO threshold or really strongly. So I hope you've seen now a bit what is meant by exploratory data analysis. We have one data table, and usually people have a tendency to say there should be one way of plotting my data, but that's wrong. You have lots of different, you can use scatter plots, histograms, you can use box plots, you can use whatsoever, and you just go through all of them and try around, and always whenever you have a feeling, I can't quite see whether this box plot might not be hiding some information, and you switch over to another one. And the nice thing is that this, in the end, it's so easy, because once you understand this way of writing your plots, you see it's always just changing little things. I change histogram for density or for whatever, and then I can look at it again. How do I change them? Your most important thing is then, of course, Google in a way. If you look here at the ggplot2 page, one thing that it gives you here is this big cheat sheet, which is a little A4 page summarizing all the geoms and how to use them. The other important thing is that it has loads of little plots. What I have wanted to bring down to you and hold up is my ggplot book, a good old-fashioned book on paperback, which has inside lots of colorful pictures of different plots in very many different ways, and then you can browse through it and say, oh, I've never knew that you can plot things that way. Let's look how it works. So the way how you learn plotting in R is you take this ggplot book and you just browse through it. And when you see a plot and say, this is the kind of plot I would need for my data, then you just turn the page and you read the chapter on how to make this plot. And usually it explains to you, well, you have to use this geom and you have to specify the aesthetics for X and Y and color and so on. So, let me quickly look through my step here, what else I wanted to show you besides obesity and so on. Yes, I took out a few other things, which I took out here, for example, that's a plot you can look at later, where I now use bar charts, and I categorized them by age groups. These are always 15 to 20, 20 to 25, and so on. And you can now already guess how this works. I've made my filter for age at least this. I put my category with the breaks. I cut the interval, the age also with this cut command into ages of length 5. And then I used my geom bar to do this, and the faceting, which again says divide it up in 2 plots for the 2 different sexes. What else was there? My bonus thing. Lecture 1 extra. So this was just this morning when I looked at it and thought, what else could I plot? And I found these other 2 columns, education. So I thought, does height depend on education? Are smart people taller than seem to be? Here now you can't quite read the Y label. This is a common problem with ggplot. The thing which I do about once every week is that I go to Google and say ggplot vertical axis labels, and Google already tells me what I want. Here you see. and I still have never managed to reply it. Every time I make the same mistake, I read here, this is how it works, and I copy this. Why is that a bad idea? Because with a stack exchange question, if you read it here, it says, I have tried this to rotate my axis and it doesn't work. So if you Google for something, you shouldn't copy and paste from the question, you should copy and paste from the answer. So. So here, and the answer was just add this little thing which says theme axis text x is element text angle 90 h horizontal justification. Once looks a bit overly complicated, but that's what we have copy and paste for. Now it's easier to see. So the categories were drop out of high school education of less than 9 years, 9 to 11 years of high school education without getting a high school diploma only, started college but didn't finish, and then finished college or higher education. So now I was looking at this for quite a while and was wondering, what does this really mean? Came up with a few ideas. One is, first it looks like it's going up a bit, but actually maybe it's staying up once you look at the last 3 lines. And the first 2 lines, people who don't have any high school education, not even 9 years, might be disabled people. So the children are already removed here. So it might be maybe disabled people, maybe mentally disabled people who couldn't attend normal school. And as you all know, this has a comorbidity which also often affects physical characteristics. So this might be one reason. Another reason might be socioeconomic status. You might know that the 2 main determinants of adult height in humans is one, of course, your genetics. Height is quite heritable if you look at their parents and at everybody's parents. And second, nutrition during the first 3 years of your life. So people who come from a disadvantaged background might be a bit weaker, might be less tall, and they might also have less chance of really following the ordinary school education. Maybe these are immigrants who came to the US only after they were adult, who grew up in a poor country and went to the US because their home country was poor. So of course, when they ask, have you finished any years of US high school, they answered no. So one thing to do, and now once we have these kinds of hypotheses, now of course we can start again and do something like, if you remember which columns I actually took out, you might have overlooked it, but I also took out ethnicity, education, and born in the US. So let's cross-tabulate education against born in the US. So enhance, file, new file, enhance, and filter. Let's only look at adult people again. 20. Let's now cross-tabulate with count the education versus the born in US. And then, of course, as might be, it would be nicer if it puts it next to each other. Let me quickly do this. Spread. Help. I should remember these shortcuts for next time, how to always quickly show you one thing, but now I have to show all panes, Ctrl-Shift. So I show you one last bit of magic. You see, this is what we call a long table. There's long tables and wide tables. What you would like to have is that we have education and then 2 columns, yes and no, and we have columns. So I want to spread born in US and N. And now what does the spread command does? You see, it spreads it over like this. it changes this long table into this wide table. So this is something which gets always is a bit a knot in your head when you want to do these two operations, spreading and gathering, and we will cover this later in the course, but it's a rather common and important operation that you want to pull data and say, I now want to rearrange my table that I don't have columns for different sample IDs, but columns for different drugs that I have treated. If, for example, you might analyze an experiment where you have put different drugs on different samples and this in different replicates and different temperatures, then you can always have to you might want to have a table where the columns are the temperatures or the columns are the drug, and you want to keep rearranging your table. If you do this in Excel, you're copying and pasting probably for hours. This way, here it's probably still simple, but it goes quite long. Now, if you look at it quickly, it's exactly how I thought. These people here are the people who haven't been born in the US, also haven't gone to high school. We now would have to look at the details of the data manual of N. Haynes, whether the question asked was actually how many years of US high school have you filled, or how many years of school in whatever country you had been living during, which of course makes an important difference to understand these things. The thing which we can now do is, of course, happily plot other things. Here now I got sort of on my box plot spread and spread all kinds of height against ethnicity, height against whatever. This was maybe the interesting, this is this one here. Here, for example, we now see that might be one interesting thing where you can quickly see. We have, I have simply filtered age, and when I said geom plot, y is the height, I want box plots, and as x I now specified an interaction between two factors. What does this mean? Well, it becomes pretty obvious once you look at the plot. It just says here, male born in the US, female born in the US, male immigrant, female immigrant, and we can see that in fact it looks a bit like immigrants tend to be smaller than US-born residents. Now we're coming in the region of statistical inference. We might now ask, this difference is pretty small. If you look at this box plot, it's just 1 or 2 centimeters. If I do a t-test comparing the two, I might find it to be quite significant. Actually, I've done this here for the women. You see here, this was my command. I filter for adult women for which I know whether they are born in the US. So born in the US is either yes or no, it is not don't know or something like that. And then I say, please make a t-test of this. And it says the t-test is highly significant, but the difference in the sample mean here, well, it is actually, it's quite some difference. It seems to be 156 versus 161. Now we can wonder about how many people do we have to look at? How will it look like if we only had compared 10 immigrant versus 10 US-born residents? Could we still detect these things? Which is, of course, the important question, how to judge sample size. And this is what I meant at the beginning with being able to use simulation. If I want to explain to you how to specify powers for an experiment, I can give a long talk with a lot of formulae, explaining to you how you calculate by imagining how your data might look like if you had 1,000 mice. But we can also take a data set like this, where we do have 1,000 men and immigrant men and 1,000 non-immigrant men. And then we can ask R to take a random sample of 10 people, of 10 immigrants and of 10 non-immigrants, compare them and check how much is the difference, and redo this. And I've done this here. You see, let me do this last part here before I finish for today. So here I've now made me 2 lists. This is height of Mexican women born in the US, height of Mexican women born outside the US. And if I now just take from these 200 things one sample, like sample 1, I use the sample command to just take 10 random women here, and I take 10 random women from the other thing and ask what is the difference in mean. It's 1 centimeter. Now let's take 10 other women, and another 10 other women, and now the difference is suddenly 2 centimeters. This is, of course, highly relevant to have an understanding of these kinds of things, because what I've just done is sort of a illustration of the following situation. You do an experiment comparing 10 treated mice with 10 control mice and report your paper and saying, my drug increases blood pressure by 1 unit. And your competing group does an experiment with 10 mice, 10 treated and 10 untreated mice. Say, this very same drug increases stuff by 2 centimeters. And now we have to say, is this statistical fluctuation or not? And just to get a feeling of how strong such fluctuation is, something like this is useful. You see, now it's 6.8 centimeters, 3, 2. Now it's even negative. And obviously, what I have done here is I used in advance the fact that I have all this data, which of course not a realistic combination. In a real experiment, all you have is your 10 mice. You don't know what the 10 mice of your competitor will do, and you don't know what their paper will say. But you can infer this. You can see how much the standard deviation among your 10 mice is, hope that the standard deviation over all the million mice you could theoretically do your experiment on is as large, and try to infer this from that. And then you will come up that the real problem is that you don't quite know how big the standard deviation is. Are your 10 mice, because if I now take this sample, if I want to know whether this mean is large or small, what I should look at is the standard deviation of them. How much are they spreading? And you see the standard deviation is 6 centimeters, 7, 5, 6, 4, 2. So the same 10 mice can have a standard deviation of 2 and can have a standard deviation of 6, which means if you draw an error bar, in this case, your error bar will be about 4 times as large as in that case. And that's something which always happens. It's completely, I will show you next lesson, how the standard deviation can really change to twice, 3 times the value if you have 10 samples. If you have 100 samples, this is unlikely to happen. And you can, using things like this, try out. Let's say you now do make an experiment with 10 mice and you want to know how much do I have to expect the standard deviation to vary compared to the hypothetical case of me redoing the experiment with 10 other mice. And using a simple simulation like this gives you a good feeling for that. Of course, instead of simulating it, you can also calculate it. That's especially useful if you don't have a modern computer, because you're in the year 1908. Your name is William Gossam. You work for Guinness Brewery and make the quality control. And instead of mice, you have foam in Guinness and things like this. And you want to know how many Guinness beers do I have to test before I can tell Alec Guinness, my boss, that this one was acceptable. And so William Gossam spent a lot of time thinking about how he can sort of know in advance how much the standard deviation might vary. And he put this all together in a handy formula, which we all now know as student's t-test. Why do we call it student's t-test and not Gossam's t-test? Because the whole idea of employing a statistician to do a scientific quality control was such a revolutionary new idea of Alec Guinness that he wanted to keep this a trade secret and told his statistician that he can only publish his result under pseudonym. So that was but what actually Gossam found out and how this t-test works, that's something we can try this way next time. So short look out into that. But by that I think I've talked an hour now, so let's finish here.
Yes. So as we understand, I was unable to follow any of your steps today. What I wanted to ask is that from what I understand, the level is quite advanced for meteorology. If you provide any more basic
You have a feeling you didn't understand anything, or you just didn't understand the commands but still understood the plots?
Yeah, of course, the plots.
Yes, but that's all I wanted for today. I'll explain a lot more next time about.
You also the circle is just an additional point, additional end.
Take a seat.
Thank you.
And you form them.
Achso, jetzt schreiben wir dich erstmal auf die Liste.
Well, there's also a select count, so it's not only showing.